In the last video, we talked a little bit about the hierarchy of structures that we encounter, or at least that we've encountered so far, them being functor, applicative, which is a middle ground, and then monad, which is quite restrictive in a way. Today I'd like to give you an example of that. So sometimes you might be able to define a monad, sometimes it might not make sense to define a monad. For example, here we have a binary tree. We've seen this type quite a few times. A binary tree of type A is a node with two recursive calls on either side of a value, or it's a leaf. This is one definition. Other definitions are available. Now, you can easily define an instance of functor for this because you just recurse down each side of the tree, applying f to every value. When you reach a leaf, you leave it as a leaf. Now, you might think, oh, well, I've got functor, I'd like to have a monad. Now, the problem with this is we don't necessarily have a good definition for a monad. We could define something that type checks. It might not be helpful, or it might not even make sense. So for example, here I can easily define return x as a node which has two leaves and the value in the middle. And I can bind a leaf with a function f by just returning a leaf. Now, if I have a binary tree which has two subtrees and a value in the middle, and I bind that with f, now remember that the type of bind, and I missed an equal sign up there, is this. So I have a function from A to B. So I can't actually map this list. So what I would have to, or this tree, so what I'd have to do is I'd have to throw away the entire tree structure and generate a new tree from one element of the binary tree. Now, that's not really great, is it? Because I could have other values in the tree that I'm interested in. I don't have a great way to combine them without just ignoring a lot of the structure and regenerating another tree, which might be the same tree, it might be something that has a similar structure to the original tree, it might be something that's completely different. It might even map a value of x just to a leaf, and so I've gotten rid of a tree and I've replaced it with a leaf. So it's not a great definition. So what do we do? Well, we might still want to have some sort of effectful computation, so we might turn to applicative. And we'll have this, oh, this should be B tree, and this one should be B tree. If I could type anyway, it would be where something's going to happen. So let's say, well, we have the pure function that we want to define. Remember, let's get that up on screen actually, just so that you can have a look at that. We have to define pure, which is A to FA. That's easy enough because we can just say that pure of the value x is equal to the same as we had for return beforehand, so we just have node leaf x leaf. And that's fine because we can just embed something in the binary tree by making its own node, and that's okay. Next, we want to define this so that if we have a binary tree of functions, then we can apply them to a binary tree of values to get a different type of binary tree. So what could happen here? Well, we could have a leaf on this side, and whatever we have on this side we probably want to return a leaf, because if I don't have a function then I don't know what I'm going to do without to the value. I can't convert something of type A to something of type B without a function, so I'm just going to have to leave that there. Similarly, if I have a function but not a value, then I can't return a function from A to B when I need something of type B, so this should also be a leaf. Next, what I want to think about is what happens if I have node, left tree, f, right tree, and I want to combine this with a node, which is a left tree, a value, and a right tree. So what happens if I want to combine this? Well, it's actually not too difficult. What I could say is I should return a node, and then I need to think about what's going to go in the left tree, what's going to go in the right tree. For the moment though, what's going to go in the middle is fairly obvious because I have a function f from A to B, and I have a value of A. So this should clearly be f of x in the middle here because I have this x and I have this f, so I'll just put them together and keep them in the node, retaining the structure of the tree, you'll note. Now, what happens here? Well, I know that on the left hand side, actually I should say that this is LTF and this is right tree f, just so that these don't get confused. So on the left hand side I have a binary tree of functions. On the right hand side I have a binary tree full of values. So what should I do? Well, I should recurse. So what I can say is LTF, and we can combine this with left tree. Similarly, on right tree for functions, combine this with left tree, or right tree, sorry. So now we can do some sort of applicative effectful programming without worrying about having a monad. So this is one case where you can't get something quite as restrictive as a monad or as powerful as a monad, but you can get the applicative value out, which is still quite useful in and of itself. So let's see if I define our deriving show. Let's save this and recompile. Oh, that's the lowercase t, so this should be uppercase. And the other two are uppercase, so hopefully that's fine now. Oh. There we go. It wouldn't be one of my videos without some mistakes. So let's say we want to let x equal, and let's define a binary tree. So let's say we have something that's got a node, and let's say we have another node, and leaf will not make it too busy. Let's say we have a binary tree of integers. Why not? Let's do something wild. And then we have a leaf here, and let's say that we have 6 here, and then we'll just put in another value on the left on the right hand side so that we have something else to work with. So I can define this as x. X is now a binary tree, and I have something to work with in REPL. But now I want to supply this with a binary tree full of functions so that we can map these things. So let's say that we have, and we'll have to copy this structure, won't we? So let's just copy this. Copy, paste, and let's say we put an n in there so this actually works. So now we can get rid of these values and replace these with functions from something to some other type. So let's say we want to do booleans. So let's say here I have a function from a to b. It's a function from int to int. Let's say that's 5. Let's say equals 5. And then let's say we have something else here, which is, oh, why not? Let's say slash x goes to x times x times x greater than 20. And let's say over here we just have something else. Let's do another lambda just for the sake of it. So we have x mod 2 equal to 0. So you can see here now I have a binary tree full of functions, and I want to combine this with my binary tree full of integers. So what I can say is x. And this will say combine these two, going step by step, recursing through, applying the function to the element and building the tree back up as you go. If I hit enter now, you can see that these have been converted to the corresponding values. So this was indeed equal to 5 because I set this to be equal to 5, so we've returned true. And I said that square value of this one is greater than 20, so 6 squared is 36, that's clearly true. And this one was even. No, it's not, because it was 7. So the applicative allows you to transform a binary tree, in this instance, with a binary tree full of functions. They don't have to be the same thing, they don't have to do the same thing, but they do have to map to the same type. That's one restriction. And you can see that in the definition of applicative. And it's a function from a to b, but it has to be wrapped in the overall structure. So you could imagine this doing something quite complex. Imagine you have different people whose data you want to transform. You have functions to do the transformations, but you need to transform it in the right places. So you build up at some sort of structure like this, and then you map it piece by piece in the way that you want to. So this binary tree could be something more complicated. This could be, say, for example, in the uni, students' information. This could be a database structure if you were so interested, and you map elements case by case. That's one thing we always forget to mention, is that SQL is a functional language. So as an aside. But this is one instance where you can't quite have a monad, but you could have an applicative. And an applicative allows you to do quite a lot of cool stuff. But that's everything for today. This was just to give you an instance of what we talked about in the last video and show you that it does actually come up while you're programming. Of course, if you have any questions about this, please feel free to get in touch. Thanks.